We'll expand sin x as a power series in this form. We'll go quite quickly because we're using the same technique as in the e to the x video, so if you arrived straight here, you might want to watch that one first. First, we'll substitute in x equals 0. On the left-hand side, sine of 0 equals 0. On the right-hand side, only the coefficient a0 survives. The other terms are all 0 because they all contain a power of x, and x equals 0, so the term is 0. This means that a0 equals 0. Now we'll differentiate. On the left-hand side, the derivative of sin x is cos x. On the right-hand side, we differentiate each power term individually as colour-coded in the video. Now substitute in for x equals 0 again. The left-hand side is 1 now, because the cosine of 0 is 1. On the right-hand side, this time only the a1 term survives, because it is the only one without a power of x to make the term 0. Then we repeat. Differentiate, following the same method as before. The derivative of cos x is minus sin x. We won't explain that here, and if you didn't know that, you should look it up. And substitute in x equals 0. Again, as before, 2a2 survives, the rest are 0, but minus sine of 0 equals 0, so a2 equals 0. Differentiate again, minus sin x becomes minus cos x. And substitute x equals 0. This time, the 3 times 2a3 is the only term to survive setting x to 0. Differentiate. And substitute. 4 times 3 times 2a4 survives. And sine of 0 equals 0. So a4 equals 0. We could carry on going like this, but we've probably gone far enough to spot the patterns emerging. The even coefficients are all 0 because they are all found from an expression having a sine function, which is 0 when setting x equals 0. The odd coefficients include a factorial term due to the successive differentiations. And the odd coefficients have alternating signs, positive, negative, etc., due to successive differentiations giving the cycle sin x, cos x, minus cos x, and back to sin x. So here are the coefficients we've met so far, plus the next few according to these patterns, with the non-zero ones, the odd coefficients, coloured. And we can write our sine power expansion as follows. It always amazes me that a simple algebraic power series can be the same thing as a trigonometric function, but there we are. And we can write this power series using the summation notation as follows. It's the sum of an infinite number of terms. The minus 1 to the k provides the alternating sign. X to the 2k plus 1 provides odd powers of x, because if you take any integer k, multiply by 2 and add 1, the result is odd. For example, k equals 1 gives the x cubed term, and k equals 2 gives the term in x to the 5th. And the same 2k plus 1 is used to generate the factorial in the denominator.